Okay, welcome to WASA Distance Education. This is MBF3C, Grade 11 College Prep Math. I'm Pete, and I'm your teacher. So, special announcement today. This is a pre-recorded class, so don't call in. I'm not there. I'm traveling. I'm traveling up north. So, but we will be back tomorrow in the studio. So if you have any questions from today's class, yesterday's was also pre-recorded. You can email me. You can contact me on Facebook, PW space WASA, or just hold your question till tomorrow, Thursday, when I'm back in the studio. Okay, so now this class will just kind of pick up from where we left off yesterday. We were just wrapping up lesson 19, theoretical probability, and then we're going to do a fairly short lesson, lesson 20, talking about probability and statistics in the media, which is really a very important topic. And sort of knowledge of that will be very helpful to you in making decisions in both your life, and it's also helpful to businesses as well. But where I kind of left you hanging yesterday because we were looking at support question 6. This is on page, oops, let's, um, this is going to be on, okay, now I've lost my place here. No, okay. All right, well, I had it. I think I probably just lost it. Oh yeah, here we go. On page 23. So this is page 23. This is unit 4. Okay. So what we found out yesterday when we were looking at this theoretical probability is that the probability of some event is equal to the number of possible outcomes. Okay? It's the sample space okay, and that is the number of outcomes that satisfy what we're looking for, right? So number of event outcomes. Well, which is a very sort of a roundabout way of saying that, for example, if we want to figure out the probability of flipping heads on a coin, then the possible outcomes, there's two possible outcomes, heads or tails, and there's only one possible event that satisfied the criteria, in this case, heads. Okay. So and that's really kind of the basic takeaway from lesson 19. Now, the other thing we looked at is that if you have multiple events in a row, right? So multiple, you have the probability of one event, and you want to know what the probability of a certain event, and then another event, I guess we could call it event 1 and event 2, just to avoid, well, okay, let me, I'm going to erase that. Okay, so I'll change colors to make it. So the probability of, say, one event, and then the probability of another event, and the probability of a third event consecutively happening, you just multiply them. Okay. Now, in the case of events that are repeated, for example, our probability of a head, then, right, the probability of a head, let's try that again. Yeah, what I was trying to say is the probability of, say, 3 heads in a row, it's just going to be equal to the probability of one head multiplied by itself, the number of times, which we have a little shorthand. Right? It's just the probability to the power of however many times we want to do it. If it's 3, power 3. If it's 5, it's power 5. A million, power a million. Okay. And I hope that you might be able to see that that number gets much smaller the bigger the power. The more probability, or the more trials we want to have of the event to be to come out a certain way, the much lower the probability. Probability of 1 is just a half, and it gets smaller and smaller. Okay, now yesterday we kind of left off with this question, which is what is the probability uh, hmm, uh, of drawing an ace from a deck of cards on 2 consecutive draws? Okay, so an ace, and that's where we were. This is support question 6, page 23. Okay, so this is page 23. So the probability of an ace and an ace. All right, well, let's think about this. How many aces, what is the probability of drawing 1 ace, okay, from a deck of cards? How many aces are there in a deck of cards? Okay, we know that there's 52 cards in a standard deck, and there's 1 ace for each of the 4 suits. So the answer is 4, which is 1 out of 13. Okay, 1 in 13. That's our probability. All right, well, what's the probability of drawing 2 aces? Well, now I think we're ready to answer that, because we know that the probability is just the two probabilities multiplied together. I'm just going to erase that because it's, oh, I used a big eraser. Yeah, that's good. All right. So it's just that 1 over 13 squared, or you could just say 1 over 13 times 1 over 13. But really, this drives home the idea that if the same probability, if we're doing the same event over and over again, then the probability is just to the power of the number of times we've looked for it. So it's going to be 1 over 13 squared, which, let's see, 13 squared, is that 1, 2, 1, minus 6, 13. I guess I should probably know my 13 times tables, 169. Not something you do very often, 169. Okay. Now, if we wanted to find out what that was as a percent, it's going to be very small. It's, well, the probability is 0.006, or approximately 0.6%, something like that. So less than, just a little over than 0.5% probability. Very small probability. Okay. And if we wanted to figure out what's the probability of drawing 3 aces in a row, right? You could work that out. It would just be, what would we have to change? We'd just change that number to a 3. If you wanted to draw the probability of drawing 4 aces in a row, right? So if you're playing a card game that favors getting aces, where aces are very powerful, you can see how low that probability is, how rarely that happens. Okay. All right. Let's take a look at the key questions now, and then we will. I think I got to go back here. Okay. Whoops. No. Forward. Okay. Keep going. All right. Keep going. There we are. So these are the key question 19, and hopefully they'll look familiar to you from the support questions. Find the probability of each situation rolling a 6-sided die. Again, is that singular for dice. So keep that in mind. It's page 23. That what they're talking about is 1 to 6, not 2. They show 2, but in fact it's just 1 die. That's a I gotta fix that. That diagram is really misleading. So what is the probability of rolling a 5? Okay, so now, so it's 1 6-sided dice, or die. Okay, so you can work out that number greater than 4. How are you going to work that one out? Remember, it's 1, 2, 3, 4, 5. So 6 And greater than, basically, there's just two numbers greater than 4. It doesn't include the 4 when we're doing greater than. All right. Now, for question 2, and this is actually, I wanted to give you an example of this because this is where tree diagrams really come in handy. And it can make the difference between getting the question fairly easily and not. So I wanted to show you this one, and then that might help you for some of the other questions. So let's take a look at question 2. I'm going to make a new page here, and hopefully you'll be able to follow along. So this is key question 2, and that's on page 23. So it says Jesse needs to get ready for school. He has 2 pairs of pants to choose from, 1 black and 1 brown. He has 3 shirts to choose from, 1 red, 1 green, and 1 white. Any combination of pants and shirts is equally likely. Use a T diagram to find the probability that he will wear a green shirt and brown pants. Okay. So the way this works then is she's got 2 pairs of pants to choose from. Okay, so let's take care of the pants first. Okay, of course they're black. All right, this is black. Okay, so those are the pants. Okay, so he's getting dressed in the dark. He doesn't know. He reaches in the drawer. There's 2 pairs of pants. He puts one on in the dark. He doesn't know. Then he opens his next drawer. Again, it's the dark. Maybe he's still sleeping. He's got his eyes closed. And then he puts on a shirt. Now, once he's got those pair of pants on, he's got a choice of 3 different shirts. Not a choice. It's an equal probability of having one of 3 different shirts. Okay? He's got a red shirt, a green shirt, and a white shirt. Now, normally we use the first letter of something when we're drawing these diagrams, which is why I laughed when we had black and brown pants. It should have been black and white pants or red and green pants or something. Anyway, I'm just going to move this part of the tree over a little bit just to give us a bit more room. Okay, so remember, these are the pants up here, and these are the shirts. So what do we do on this other side? Well, he's got his pants on, the black pants on that particular morning, but guess what? If he puts on the brown pants, he has the same probability and the same event space as he had for the other pants. A red shirt, a green shirt, or a white shirt. There you go. Okay, so now let's take a look at this. What are the total possible number of events, or what's our sample space look like? Right? Well, our sample space has 1, 2, 3, 4, 5, 6 possible results, right? There's 6 possible outcomes of him getting dressed in the dark, putting his pants on, putting his shirt on, and walking out the door. He's either going to be wearing black or brown pants, and he's going to be wearing one of a red, a green, or a white shirt, and in some order, right? So there's 6 different outfits that he can be in. So now that we've worked out the sample space, let's find out what the outcomes are. Right? How do we come up with the outcomes? Well, it says A, use a T diagram to find the probability that you wear a green shirt and brown pants. Okay, so first of all, now our event that we're looking at has brown pants and a green shirt. There you go. Now tell me something. Is there another brown pant green shirt combination? There isn't, right? There's no brown shirt possibility on the, there's no brown pants possibility on the left-hand side of the tree because he's wearing black pants. And on the brown side of the tree, where he's wearing brown pants, there's only one branch that has a green shirt. So of the 6 possible outcomes, there's only one way that little Jesse, is that a he? Oh yeah, little Jesse can end up going out in brown pants and a green shirt. There's just one of those 6 possible outcomes. So you can work out the probability of that now, right? So the probability of the brown pants, brown, yeah, I'm going to change that to brown and yellow pants or something like that. And the green shirt. Okay, so it's the total possible outcomes on the bottom and the number of events that match that possible outcome on the top. Okay, so that was A. Now let's take a look at B. Now the nice thing about making a tree diagram is that we've already made it. We don't have to make another one. Okay, I know it says use a tree diagram. You have one, the one you made for part A. Okay, so don't waste your time making another tree diagram. So for part A, it says use a use a. It's all right. This is pre-recorded, so I can actually watch myself doing dumb things. Use a tree diagram to find the probability that he will wear black pants with any of the 3 shirts. So now, was it black pants? Black pants. So now, okay, so how many possible outcomes? He's got a black pants, he's got another black pants, and he's got another black pants. You see? So you don't have to make it, you don't have to draw another tree diagram. Okay, so from the total possible outcomes, the probability that he's wearing black pants, black, that's all right. Black pants, and then, it's either going to be red, green, or white. So any shirt, basically. And then you could figure out how much that is. Okay, so that's how you use one of these tree diagrams. Now, I did a kind of a top to bottom tree diagram. The one that they show in the book is left to right. Some textbooks show the left to right one. Honestly, I think that if you're doing them by hand, top to bottom is easier, and if you're making them on a computer, probably the vertically, the left to right ones are easier. So just do whichever one you want to do, though. So now for question 3, I think you can maybe you can come up with a tree diagram, or maybe not. It says each letter that makes the name Brianna, Brianna, are put on cards and placed in a box. State the probability of each event given if one letter is selected at random from the word Brianna. An N. Okay, now you got to keep in mind that in that case, there's more than one possible event that satisfies the, right? Because there's more than one N. A vowel, okay, so I don't know, a vowel, A, E, I, O, or U, okay, or an R. And again, I think there's only one R in there. Okay. So hopefully you'll be able to work your way through those. Okay, and then the rest of them I think are pretty straightforward, the ones that we've looked at. Okay, so that wraps up our look at theoretical probability. It was just a quick kind of look at it. There are whole courses you can take where you really go into a lot of detail, and it'll really help you kind of understand probability and in some ways statistics as well. Okay. Now we're going to turn our attention then to lesson 20, the last lesson in the course. That's right, we're done. And because this is being pre-recorded, it's not quite the same day as you'll be watching it. But if you're watching this on Wednesday, it means that we're on class 3 of week 8. There's only 9 weeks in the course. Next week, for you, is a short week. There's only 3 classes, which means that Thursday's class, and then there's only 3 other classes. So there are 4 classes left after today's pre-recorded class. What we'll be doing for the rest of those, we'll take care of anything that's kind of left over tomorrow if there were any questions, or I assume I'm going to get finished everything today. And then we're going to start our review. Okay, so we'll review everything in the course with an idea that we really want to do well in the exam, and we want to make sure that we cover everything. Okay, so now, and one of the things that we'll talk about also is what there is a formula sheet in the exam, so you'll be able to have something to kind of look at have their formulas so that you don't get nervous and forget the formulas, especially those ones like the compound interest and um, amortization, and sorry, annuity formulas. Okay, so that's what we'll be doing for the rest of the course. So it's a review. It's very useful. I think I'm gonna go over all of the material with sort of an idea of where students sometimes have trouble um, in a class. Okay, so let's take a look at lesson 20 then, and that's on page 25 of Unit 4. Okay, here we are. So probability and statistics in the media. Okay, now the media, we're talking about the internet, of course, websites, things like that. Okay, you may, for example, you'll say that, for example, eating a certain food triples your chance of having this medical problem. Okay, you may have seen that, right? Eating certain foods, right? It triples your chance, or it doubles your chance of something, which sounds really scary unless the chance of that thing happening is 1 in a billion, right? Because 1 in a billion is a very small number, and doubling your chances, 2 in a billion, still a small number, right? 3 in a billion, 10 in a billion, still a very small number. And that's the problem with statistics and probability in the media. They almost never tell you what the base number is. They'll only tell you something like that, right? Your chances of, having some, of having some medical problem or having some difficulty, they'll double or triple or quadruple, but they don't tell you what that original probability was. If your original probability was 1 in 100 and that doubles to 2 in 100, okay, I'm paying attention, right? But very often they're talking about doubling something that is so small that it's almost insignificant anyway, and doubling it doesn't make it any, right? And this also works, it can work in your favor as well. If you think about buying lottery tickets, right? And, the lotto is 649, right? So you buy the lottery ticket, and your probability is it's very small numbers. It's like 1 in 14 million, I think, to get all 6 numbers. It's a very small number. Buying 2 tickets doubles your probability of winning, but it's still a very small number, right? And really, no matter how many tickets you buy, you really can't improve your probability. All you do is, well, if you look at it as a game, then you just increase your fun, because now you have more numbers to cross your fingers over when they're making a draw. Okay, so that's something. If you're aware of the fact that probabilities, doubling probabilities still make very small numbers, then it can really kind of help you. Now, another thing that we see quite a bit, and we'll actually look at that a little later, is weather predictions, right? So they're not going to say it's going to be sunny tomorrow. They're not going to say it rains tomorrow, because really they use models, they use mathematical models. So instead they'll give you a probability. They'll say POP, probability of precipitation, 60%. Right, or 20%. Usually it's something in that range. If it's a really low probability, they might say chance of rain or something like that, chance of snow. And that's just because, maybe they look at the fact that over the last 90 days, when these weather conditions occurred, the same weather conditions occurred, or maybe last year when these weather conditions occurred, it rained 60% of the time when this happened. Right? Maybe that's how they come up with it. Okay? So when they're saying a probability, even if it's a very high probability, it doesn't necessarily mean it's going to happen. Okay? And then, of course, you go Las Vegas, where they have lots of gambling and stuff like that, playing cards, things like that. A lot of that is based on a study, a very careful study of probability. Okay, it's interesting to actually learn about our knowledge of probability. A lot of it does come from gambling, and a lot of that research was sponsored by governments or leaders who wanted to make sure that their state-owned casinos always came out on top. But sometimes we can use statistics and probability in sort of a beneficial way. Okay? So the course material gives you a case study, and I think they actually use that as part of your key questions as well. Um, they talk about this OnStar service that General Motors has in their vehicles. So basically, it's like a cell phone, so maybe it doesn't work so much up north, but down south where there's cell towers just about everywhere, um, the vehicle has a way of making a phone call, a data call, basically um, to General Motors headquarters, OnStar headquarters, and to sort of explain what's going on. There's some emergency going on with the vehicle, right? They also have a cool thing about being able to unlock the car from the outside. Now, back in the day, I guess this was a pretty big deal. Now that we all have electronic locks, maybe not so much. But I guess people forget their combination sometimes. But for example, if the airbag in the vehicle goes off, the OnStar will actually call, right? Because the assumption there is that if the crash is serious enough to cause an airbag to deploy, chances are they're going to need an ambulance or going to need some, firefighters, police, whatever. Okay. Crash notifications. Okay, I'm not sure why these numbers are different. You'd figure they'd be closer. Emergency service calls. Now that's where somebody in the vehicle pushes the button. I have a flat tire. There's smoke coming out of my car. The check engine light's been on for the last 3 days, right? That's an emergency service call. Okay, the car just stopped. Okay. Now another one here, they call them Good Samaritan calls. So that's where they're push the button on the vehicle, and there's an actual OnStar button inside the vehicle. You may have seen these before. But they don't get much use up north because we don't have the same kind of cell coverage. Um, so the Good Samaritan call is when they're going by and maybe it might be an elder who's driving or an elderly couple that's in a car, and they say, hey, we just passed by and it looks like somebody's has a flat tire. It looks like someone's in the ditch. So they can't really stop and help, which is what we normally do up in the north. If we see someone stuck, we stop, right? If we can. But sometimes they can't stop, or down a little further down south, it might not be so smart to stop. So, but they push the button and they get them help anyway, right? It's the same thing. They get the police there. They get a tow truck. Stolen vehicle location assist. So that's where, somebody gets their vehicle stolen and then they call the police and the police ask OnStar, hey, where is this car now? Right? And then a lot of remote unlock calls. Again, I think that these vehicles all have touchpads on the driver's side door, but for some reason, maybe people forget maybe they forget their password or passcode or whatever it is, and they're basically asking you OnStar people to unlock the vehicle, which is great. I mean, it sure beats having to get someone to come and unlock it using one of those Slim Jims or whatever they call them. And then an awful lot of requests for roadside assistance. So that, it's something, flat tire, maybe the car slipped off. And you never know, right? You just never know when your car is going to slip off into the ditch. I've been pretty lucky and pretty careful, and yet out of the blue, a couple weeks ago, I was out on one of the forest access roads, and I was actually leaving. I was going up a little hill, and for some reason, my car just slid a little bit sideways, and then I just couldn't move after that. I slid right back into the snowbank, and but somebody came along. See, I didn't need OnStar because in the north there, just a truck will come by. The guy had a winch he had a tow strap, sorry, and just pulled me right up. But down south, people don't have big trucks, and if someone's stuck in a ditch, they need to call a tow truck. And then look at this pretty big number. Requests for route assistance, which is a nice way of saying directions, isn't it? Right? Okay. And again, we don't get lost very much in the north here because we kind of figure out where we're going before we go. But down south, there's so many roads and so many turns, and they'll get lost quite a bit. So we can actually use all of this data then to work out some statistics, right? Using the above list statistics on GM's on-star calls, create a list of probabilities for each type of call. Okay, so probabilities, wow. So remember that the probability of an event is the number of times that event happens, basically in a sample space, divided by the total number of events. Now they gave us the total here, right? So if I wanted to know what is my probability of having an airbag deployment, right? Call, right? So this is the there's an operator sitting there at OnStar. There's a bunch of them, right? What is the probability that a call will be related to an airbag deployment, right? Well, I just said 1,000. Okay, sort of tipping my hand a little bit here. What I meant to say was the probability of airbag. Well, okay, probability here. Okay, probability of an airbag deployment, and it happens 1,000 times out of the 412,025 calls. 1,000 of them were airbags, right? Deployments. So now we can actually work out the probability of that. So it's just 1,000 divided by 412,025. Okay. Now this is a very small number, and it's actually given me something in scientific notation. E to the minus 4. So it's 2, 4, 2, 7. Now when it says to the minus 4, you basically go 4 hops to the left. So it's 1, 2, 3, 4. Whoa. So there you go. That's a very small number. Okay. And all right. I think I'm going to try the eraser thing. Okay. Hopefully this will work. Nope. All right, there you go. So even if I make that into a percentage, it's 0.024%. So not even 1%. A very, very small number of their calls are actually airbags, right? So that's how we can work it out. Well, I'm going to just make a new page here. Actually, I'm going to extend this page. I think we could probably do it that way. But what will actually be a substantial probability, the highest probability? The probability, I think, of a request for route assistance, directions. Okay, so the probability of that being a request for directions, 329,000 requests out of the 412,025 calls. So now we can work out that that's, if you were an operator at the OnStar Center, 329 divided by 412.25, 0.798, or basically, approximately 80%. So 80% of the calls that you're going to get as an operator for this OnStar service is going to be for, a help I'm lost type question. Now, again, we're talking about down south, right? People don't really get lost on the winter road. Or they don't get lost going, between Sioux Lookout and Dryden. But down south they have all these roads and bridge. They have turnoffs and exchanges and 16 lanes going in each direction. It's crazy. So it's very easy to get lost. So down south, I got lost the last time I was down there. I'm driving a U-Haul truck. I could have used this OnStar. Trust me on this one. You drive a U-Haul truck, it's really hard even to pull over and ask for directions in a U-Haul truck. So this is what we do for probability. So that way, when maybe there's a specialized operator that knows how to help people who've been in a crash, right? But you can work out that 80% of the operators don't really need that special training, or 80% of your operators have to be trained to help people with directions, right? Rather than helping them with a crash or helping them with first aid or something like that. Okay, so that's how the company can make use of that, right? And companies actually use this sort of data, right? They will figure out the types of calls they get, right? If you're a little older, like I am, you may remember there was a time when every single ad on TV talked about 1-800 number. They always gave you the 1-800 number on the package. If you have any problems with their product, call our 1-800 number. And it was very popular back then because what companies were finding out was that a lot of people would return a product. They buy a computer, they try it, it doesn't work, they return it. And what they found out was that most of the time it was just that the people had a question. There wasn't anything wrong with it. They just had a question and they didn't know how to get the answer, so they just returned it. So they started putting the 1-800 number on stuff. Based on that analysis, saying, well, if we had someone that could answer their question, they probably wouldn't return it. Okay, and so companies do that. Nowadays, everyone has the internet, and as a matter of fact, they even have, I've seen packages, you go into the store, and they have a little, it looks like a barcode, but it's square, QAM code, little square thing. It says scan here. So you put your phone up to it, you click, you press the button, and it takes you to their website. So if you have any questions about the product before you even buy it, they're trying to help you. And that's probably based on them doing a survey, right? Maybe they did a survey of potential customers, and they noticed that maybe half the people who were looking at the product walked away without buying it. And then when they asked them, a lot of those people might have had a question, but they didn't know how to get the answer. So by putting that link right on the box, then the person can get an answer right away. Because if they go and maybe they'll forget to look it up later, or maybe they won't come back to buy it. So this is statistics kind of in action, and probabilities put in action. Okay. Now, for our look at OnStar, we can do a few of those, right? What type of call has the lowest probability? If you were an OnStar operator, what's the probability that the next call would be a request for route assistance, which is actually, we worked it out, it's 80%. If we look at the next page, you can see that they actually have the probabilities here. So the airbag deployment's fairly low, not even 1%. Crash notification, much, much smaller. Mostly it's emergency service, car breaks down, people slide into the ditch, right? Something like that. Headlights go out. The Good Samaritan calls, that's where it's not for you, it's for someone else. Even stolen vehicles, which I think they would probably try and sell you that, saying, yeah, if your car gets stolen, if your truck gets stolen, you'll be able to locate it very easily. But really, it's very low probability. It's not, you're more likely to be locked out of your car, or way more likely to get lost than have it stolen. Okay, or roadside assistance, which is mostly going to be flat tires, right? You drive over a nail or something like that, and then and it's nice to have that, right? Because if you travel a lot, again down south, if you travel a lot, you don't know where the tow service is. Maybe you just want to get your tire fixed and get on the way. You don't want to have to stop anywhere. So it's nice to have that. You push a button and boom. Okay. Yeah, so they're going to give you the information there. And then the support question gives two examples of where statistics are used in the media. And, I think that will kind of vary. Let's take a look. We have a little bit of time here. So I'm going to show you a couple that I kind of like here. One of them we talked about, this is the weather. This is, by the way, the government weather, weather.gc.ca, and then you find your city. If you're using any other weather service in the north here, you're using this. This is where they get their information. It's just that they give the wind chills and the dew points and the sunrise and sunset. Whereas All the other sites give the same information from this, but they don't. Weather Network, they give all this information, but they don't give you all this extra. Anyway, the reason I wanted to point this out is this. Now, I know that these are this week's dates. Remember, the class is pre-recorded, or for you, it's last week's date. So notice that on Monday, let's take a look here. Monday, oh, look at that. It's going to be, maybe it's going to rain. Well, I don't know what it's going to be. It's got clouds, it's got a sun, it's got some rain, it's got some snowflakes, and then it's just 40%. So there's a 40% probability that one of those things is going to happen. So let's see what it says. A mix of sun and cloud with a 40% chance of flurries or rain showers. Okay, so there you go. And they're not even telling me whether it's flurries or rain showers, which is kind of a big deal, right? Do I need my snowshoes? Do I need my umbrella? But they are at least telling me there's a 40% chance that something's going to be falling out of the sky. So I need to be prepared, right? I'll wear rubber boots. Um, but this is a fair distance away. So, for example, the one on Wednesday, 60% chance of showers or snow. But that's for right now. It's almost a week away, and well, okay, 6 days away, 5 days away. Um, that's going to get closer and closer. Going to get more refined as they get closer, right? So the probabilities they give us for Monday are better than the ones they give us for Wednesday. But you see that that's used quite a bit in the right, used quite a bit in the media. Okay, so now if you wanted to look up, statistics in the media, uh, and you could probably find some pretty good websites on that. Oh, yeah, look at that. That's our course, but a different version of it. Okay, so, okay. Well, not really. Um, okay, so we can, do that misleading statistics in the media. And, it's the media uses it, not always even necessarily deliberately, but, sometimes our leaders will give us statistics that are a little dodgy. Um, so we can take a look at some of these. Okay. Ah, yes, more than 80% of dentists recommend Colgate. Um, so, yeah. So I guess the story behind that is that the way the survey was conducted gave a kind of a false impression, gave a statistic that wasn't quite reliable, right? And this is what we're talking about, collecting data and how we have to be really careful when we're doing our surveys. If we want reliable data, we have to be very careful, right? It's the if we ask elementary students, actually, if we ask high school students if they want homework, chances are they're going to say no, right? So if we are trying to make decisions about homework, we can't really just ask that question. We have to ask more focused questions. Would you prefer, one assignment and then you have a week to do it, or would you prefer a bunch of smaller assignments? Something like that. How much homework is too much? Even then, we got to be careful about that. But okay, let's see. What else? Yeah. So I don't know what they're trying to show us here. Misleading statistics in the news. Um, Small business survival rate. So they are showing different kinds of statistics. Kind of hard to see what their point is there. But anytime you see a graph, you want to make sure that a graph has all of the things that you expect to have, and we talked about that um, in the first part of this chapter, sorry, unit. In that the graph, it has to have a title, it has to have labels, and it has to have a scale on both axes. And if there's a number or a sort of a measurement associated with one of the axes, then you also have to have your units as well. Now in this case, it looks pretty good. They have percentages, right? Um, and they have years here, so not so bad. They're not actually explaining here what the problem is. Okay, okay, they're all right. They're talking about an ad here for Centrum, I guess vitamins. 9 out of 10 Americans don't get all the nutrients they need from what they eat. Um, and there you go. So, and what the actual the reality uh, sort of they misstated the value of the data, right? Saying, well, just because people don't get right, just because people don't get a certain number of vitamins from their food doesn't mean that they're vitamin deficient, right? Um, on a particular day. One-day measurement's not a good indication of diet, so there you go. The data they collected was maybe a little dodgy. If you're going to survey people about their eating habits, standing outside of McDonald's and asking them what they had for lunch is probably not a good example of, a good reliable survey to find out what they eat, what their actual eating patterns are like. Okay, and then adequate nutrition can be obtained from less than the recommended number of servings, right? So, the diet people and the vegetable people say 5 servings of vegetables, right? But maybe you have 3 servings of vegetables and a big jar of salsa, which has a lot of vegetables in it. So that's the sort of thing where it can be misleading if we just focus on one thing. Okay, so yeah. And yeah, so there's a lot of this in the news. Just be if you're listening to a statistic on the news or in an advertisement, just ask yourself that. How is the data collected? Why? What is your point of view? What could be wrong with that? What could be wrong? Is it the statistics? Okay. Well, misleading data. Okay. Let's I don't want to pick on any of the news. Um, oops. No, don't want to do that. Oh, okay. Okay, yeah, so they're okay, well, we got okay. All right. Yeah, so here's an example I think where they're trying to show uh, a graph here. Um, so if you look at this, um, yeah, you can sort of see there is a problem. This shows 2,000 metals, almost 2,000 metals. 1, 2, 3, 4, 5, 6. So each metal out of the almost 2,000 uh, corresponds to about 300 metals, right? But well, yeah, that's actually not so bad. But there you go with French. If you looked at that, so each one's about 300 metals. You would expect that they would have about 900 metals, but they only have 523. So, yeah, the scale of the graph. Now this is not a bar graph. This is a pictograph. But there are rules for pictographs where each unit, each item is supposed to represent something specific, right? You can't just arbitrarily say, well, it's 300 when we're doing the USA and it's 200 when we're doing Russia. It doesn't work that way. So, okay. So anyway, you could have a chance to explore these ideas on your own, and I think if we take a look at the key questions, I think that for this last unit, the last lesson, um, you'll be going off and exploring things. So the key question, if you were a statistician and wanted to relate to people some information about a topic of interest to you, what steps would you have to follow in order to be able to report your findings? Interesting. Okay. So what do you think? Um, So this is a pretty open question, isn't it? So I think that they would be looking at um, if you wanted to look at an event, you wanted to look at probabilities. I think that you would have to have maybe a clearer description of the event. If you would have to look at the total number of outcomes, let's see, you would want to have graphs, maybe charts, right? Some sort of visual aid, right? Hmm. Kind of an interesting, kind of an open-ended question. Um, Find any example of statistics in the media being used to mislead or misrepresent statistical information. Well, the news, if you go on there, I didn't want to pick on any particular news organization, so I didn't click on some of the links that we pulled up, but you can go and you can look and see. I think if we watch the news, you think that they all and I don't know that they do it deliberately, but they all kind of, the statistics don't always come out. They want to be able to present their case. They want to be able to support whatever story they're talking about. And sometimes they just don't quite get the statistics. They're the people who are preparing these things. They're not necessarily from really strong math backgrounds anyway. So sometimes they'll just inadvertently misrepresent things. It's harder to say that they did it on purpose, but it should be pretty easy to find. Go onto YouTube or go onto Google and find, do a search for that sort of term. Okay. And then the next one, using the OnStar example, make three conclusions that you could claim based on the probabilities, right? So, you know, more, twice as many people have Good Samaritan calls than something else, something like that, some statistical conclusion that you could make. Okay, and then again, make a misleading statement. Okay, your probability of having an airbag deployment is twice that of having a crash call or something, right? That sort of thing. When the probabilities are actually quite low for both. Okay, well, I think that's pretty well wraps that up. So we'll be back live tomorrow, and we'll start a review tomorrow, wrap up anything that is left over, and yeah, so that's it. So thanks for joining us today, and we'll talk to you tomorrow.